here are two different diameter vascular grafts that we built. This one is made of smooth muscle cells. We can add the endothelial cells either by perfusing this structure or building it in a more complex manner. Adding the endothelial cells is not really that difficult. So here are the vessels. What comes next? They have to be trained. They have to be matured before the surgeon will even talk to us. We have to go to the surgeon and tell the surgeon, okay, the burst pressure, the compliance, the suture retention strength are appropriate for you to implant. And this is where we are right now. So we put it into a bioreactor. Those are special purpose devices that maintain near physiological conditions for the biological structure. And this shows two ways of attaching our vessels to the perfusion system, and there we spent 3 months. This is incredibly difficult to do, and finally we ended up with this method with two kinds of tubes, outcome tube and incoming flow. The diameters are different. Anyway, let's not get into the details, but this was pretty frustrating. Now we have overcome this difficulty, and here is, I hope it will work. There is a vessel in the bioreactor. It's being perfused, and you should see it's pulsating. I'm not going to let this go forever. I don't know whether you can see that. Eventually it will go. Okay, now you can see. So that's the way you train the system, and you measure the compliance, you measure the burst pressure, and it takes about a month to get to that level where we can say with confidence that the biomechanical properties are right. Now, we can do other things, not only tubes. Here is a segment, a cardiac sheet that one can use a patch, and you can see this part of the confused system. The contractile properties of this cardiac construct is not lost in the process. Once those binding particles made of cardiac cells fuse, it takes about 90 hours for them to synchronously beat. And they do beat, and you see the nice the sequence, and this has been implanted into a chick. Nope. And finally, it's the latest and very exciting direction that we're taking. Here I can't tell you a lot because this is being patented as I talk. In nerve regeneration, there are serious problems. We don't really know how to do it. It's a holy grail of tissue engineering. Just to remind you what the structure of a nerve bundle is, it is pretty complex. It's not it's a tubular structure, but not as simple as a blood vessel. There are fascicles, several of those internal channels inside the bundle, and then the myelin sheath composed of Schwann cells, and finally the axons. So this is what has to be mimicked, and the regeneration is not, we don't really know how to do it. The gold standard is to take out, again, a piece of from you. That has serious secondary effects, morbidity, inflammation, etc., etc. If the gap is not too large, the two ends can be pulled together. Needless to say that none of those solutions are ideal. So we embarked on autologous nerve regeneration, take the patient's own cells, and in fact here we use stem cells, and we mimic this structure. We tell the computer to print a structure like that. Here is the final product, and this is implanted into an animal. And hopefully next time we meet, I can tell you what the outcome is. Actually, I know to some extent what the outcome is, but I can't disclose it. It's very promising. So this is just a glance into what we can do, and just to save time, I'm going to put all those up. You can read them. For me, I think the most important message maybe for me is this, that there will be a way to produce organs by tissue engineering methods. Of course, we're not yet there. The fact that we can make arteries and arteriovenous shunts where we are right now, that does not mean that we'll anytime soon we'll be able to make a full kidney or something like that. However, that kidney, which eventually will be engineered, doesn't have to look like your kidney. That is the result of many, many, many millions of years of evolution. If it fulfills all the functions that your kidney does, then it will function as a kidney. So the proverb, if it looks like a cat, if it acts like a cat, then it's a cat, in this case, does not necessarily applicable. So if it acts or functions as a kidney, then it's a kidney. And finally, there are many students involved in this